And welcome to the latest installment of the 2DCC webinar series. Today we have Dr. Jun Zhu from Penn State University. She is Associate Professor of Physics here, and she'll be giving a talk on topological valleytronics and bilayer graphene. Jun?
Thanks, Kevin, for the introduction. How many people here are physicists? Okay, non-physicists? Did I miss anyone? Anyway, okay, so if you're from the physics department, you have probably heard part of this. I apologize for that, but hopefully this is from a different angle, and I'll try to make it more electronics oriented. Okay, so I want to talk to you about Valleytronics bilayer graphene. You will see why that word topological is there. It uses topological system to perform the operations. Let's step back and think a bit about how electronics operate. They operate on different degrees of freedom. You might not think about it that way, but MOSFET that we are used to, or it's in our computer, turns on and off a charge current. Okay? So it's the charge degrees of freedom. By using a gate, and that puts an electric field to control the charge degrees of freedom. Spin responds to a magnetic field. There's a magnetic tunnel junction, which we already have in our computer as the memory storage unit. It operates on flipping the directions of the spin back and forth. There's something that's being researched on called a spin transistor, which attempts to use spin-orbit coupling to change the spin relaxation and then turn it on and off. So this is not product yet, this is research. So can we use other degrees of freedom? In particular, can we use this new degree of freedom that is ubiquitous in hexagonal two-dimensional materials called valley? Can we make something that is valley controlled, therefore valleytronics? So that's what we're going to do today. A lot of people here work on two-dimensional materials of various format. So this field has mushroomed since 2004, 2005-ish, when graphene was first discovered. Now you have a whole family of two-dimensional layered materials that cover from all the way from insulator to superconductor. And there's a lot more ways of constructing these materials. So what I'm going to focus on today are heterostructures that combine these two top constituents, graphene, or specifically bilayer graphene, and also hexagonal boron nitride, which is a large gap insulator. I want to talk to you what we can do when you can make a very sophisticated structure that encompasses these two materials. So what you see here is a device with different layers that we pattern lithographically with gates at multiple levels and with very tight dimensions. And I want to show you what happens when you can do all of that. Here, the hexagonal boron nitride is there to encapsulate the graphene so that the quality is high, but it also acts as the dielectric so that you can pattern gates above and below it. So coming back to this concept of valley. Valley are pockets of electrons and holes in the momentum space. Valley is not something that is unique to two-dimensional materials. A lot of materials have more than one valley. Silicon, for example, has the 6 valleys over here. So why do we hear about valley now? So the trick here is that, for example, silicon, the 6 valleys are equivalent. In other words, the physics does not actually distinguish different valleys. We have 6 copies of the same thing. And that is not the same in a two-dimensional hexagonal lattice. So here, that's the mothership of everything. This is a monolayer graphene. I've colored these carbon atoms, A and B, but they're all carbon atoms there. Just there's the A sublattice and the B sublattice. So plotted here is a band structure of graphene. And you can see that I've colored sort of two kinds of bands over here interlining. These bands are formed by the bonding and the anti-bonding orbitals that force the electron of the carbon that sticks up and down the plane there, the PZ orbital. The other three are forming these three in-plane bonds. So there are two ways of forming these orbitals. If you focus on the physics that's close to these corners, that's where the Fermi level is with the dope graphene. So that's where the low energy physics is, and that's where a lot of the properties of graphene come from, physics around these points over here. You notice that really there are two kinds of positions, K and K prime. This is the Brilliant zone here. You can see that if I'm looking at a black point over here, if I look to my left, I see a red orbital, that's the pi star. But if I'm looking at this white dot here, that's K prime, I look to my left, I see the blue one. Okay? So something is different. The bands are different at those 2 points. And if you don't know anything about the high energy bands, but simply take a cut near E equals 0 over here, you end up with the Dirac bands that we are familiar with. Dispersion looking like a light. There's no band gap. That's what happens at K. This is what happens at K prime. This is the only Hamiltonian I'm going to put in this whole talk. This is just to show that the physics is different for K and K prime. You see, I have an index here for the two different values. So something else we can learn from this low energy Hamiltonian is if you look at the wave function of these bands, they occupy the A site and the B site equally. So the wave function looks like a spinner, not real spin. It's a pseudo spin that tells you how the A and B occupation changes. And it's 50% on A and 50% on B with some phase angle, but the occupation is equal. So why not? Because A and B are both carbon atoms, right? You have a symmetry, inversion symmetry, between the A sublattice and the B sublattice. In fact, it is this symmetry that gives you this zero band gap of graphene. It's protected by the symmetry. Now, if you break it, then you get a band gap. How do you break it? Well, you can, in fact, put different atoms there. Hexagonal boron nitride, right? Boron, nitrogen. That's very large gap insulated. Semiconductors like moly disulfide, calcium diselenide, a lot of the materials that people in this room work on also fall into this category. You can see this resemblance here, except one is moly, the other one is sulfur. So we end up with a gapped spectrum, K and K prime. But you may not realize it as, for example, there are other systems that also fall under this category. Graphene on a boron nitride lattice that forms a moire pattern falls into that category. And also a piece of bilayer graphene that you can gate. So I'm going to be working on this one here. So I'll give you a little more background on what bilayer graphene is. So that's the monolayer graphene. This is Bernal stacked bilayer graphene. Play you once more and see how the top layer moves and stacks with the bottom layer. That's how they look. You take it out of a bulk graphite crystal, put it on a SiO2 substrate. So the atoms are stacked in this way. You can see that there is an inversion symmetry between A2 and B1. A2 and B1 are responsible for the low energy bands of bilayer graphene, which is gapless. If you break that symmetry by, say, applying an electric field, you give A2 and B1 different on-site potentials, you create a band gap. Exactly the same way that moly disulfide has a band gap. It's due to inversion symmetry breaking, right? So how big is this band gap? This band gap is tunable by the applied electric field. It could go all the way up to about 250 millieV. So in our lab, we can actually measure this fairly accurately with transport studies these days. It could go all the way up to about 200 millieV. So this is something that will come back later. Okay. So coming back to Valleytronics, now that we've got different values, K and K prime, if you want to make something that operates on them, you want to ask what are the properties that are different and how do you manipulate them, right? Because Valleytronics is the Valley contrast in physics and detection and manipulation of that. So I'll first talk to something, mention something that a lot of people know about, that you can use light of opposite polarizations, circular polarizations, to couple to the K and K prime value of, say, moly disulfide, right? So why is that? So it turns out that this material, moly disulfide, has an orbital magnetic moment at K and K prime. And that orbital magnetic moment is opposite in K and K prime. So that, together with the strong spin-orbit coupling in this material, gives you this energy split state with angular momentum quantum numbers. And if you now work out the optical selection rules, you realize that transitions in the K value, that and that, involve, let's say, left polarized light. Delta Mj equals -1, whereas transitions here involve right polarized light. Delta Mj is +1. So you can use light of opposite polarizations to couple and address different values. That's one way of doing it. And you may wonder, moly disulfide is not a magnetic material. Why would it have an orbital magnetic moment? It doesn't have a net magnetic moment, because time reversal flips the sign of that moment in different values. You end up with net zero, but it has non-zero orbital magnetic moment. In fact, you can think about that as somehow it's experiencing a magnetic field. That magnetic field is in the momentum space. We call that a Bilayer curvature. Bilayer curvature is non-zero at K and K prime point if you have a gap here, and points in opposite ways in these two values. So where does this come from? This comes from how the electrons actually organizes, wave function organizes itself in the momentum space. It's sort of, I've drawn some pseudo-spin here. I hope you can kind of get a sense that there are some whirlpools going on at those 2 points. And that's what's generating the non-zero Bilayer curvature, and that gives you the non-zero orbital magnetic field. Okay? So the next thing you might think about is, well, what happens if you have a magnetic field? If you have a magnetic field, you have a Hall effect, right? So if you're in real space, you apply a current in a non-zero magnetic field, real magnetic field, your electron spin, depending on whether it's an electron or a hole, goes one way or the other way. It doesn't care about that. It cares about charge. This Bilayer curvature is the magnetic field in the momentum space. One can, in fact, write down an equation that really looks like the Lorentz force in the momentum space, where if you pass now a current, this should be not zero here. This box here is not zero. Electrons in K and K prime express the opposite Bilayer curvature, and then would end up on opposite side of the sample. That's the Valley effect. How do you actually detect that? Because they're both electrons. You wish you have a Valley detector that could tell the difference between K and K prime, right? So there are a couple ways of doing it. First one is if you could create a net population in K or K prime, then you can detect the population difference. So this is optically pumped using circularly polarized light. We can select one valley to pump, and then you can measure the voltage that's accumulated due to the electrons of that valley. So optical pumping, electrical detection. So this was done by a colleague in the physics department, Kink when he was at Bernal. So that's the first way of doing it. Second way of doing it is to do a pure optical detection. So these electrons, after all, couple to light, right? So one can measure the Faraday rotation of these two different valleys, and then map out the contrast. And then indeed, there is a contrast if you have accumulation of one valley versus the other on different edge of the sample. So this is an experiment done in Mack and Chern's lab here at Penn State. So both detections involve light of some sort. Okay? How about electrically generated and electrically detected? That can also be done, although the signal is much weaker. The idea is that you apply a current here, and by virtue of K and K prime being K and minus K, you would have a slight population difference between those two valleys in order to push a net current through. And that would generate a slight valley current here through the valley Hall effect. And you can convert that valley current back to a voltage signal on this end via the inverse valley Hall effect. Kind of like how the spin Hall and the inverse spin Hall worked. So this experiment has been done on a few materials, gapped graphene and bilayer graphene. Problem is that the net polarization, valley polarization, is always small. Right? You only need a slithering of electrons near the Fermi level to participate in conduction. So the bulk majority of them are sitting there, and your net polarization is a tiny fraction of the whole electron population. So can we do better than this? You scratch your head and think about it a little bit. It's really not an easy problem. So I wish I had a valley magnet, just like magnet, where you can just polarize the spin. Right? So valley is, after all, in the momentum space. And it's not easy to generate that polarization. If you're able to couple something to light, you have a little bit of easier time. But even Valleytronics using light is not something that has been done. If you want to ask for a device that doesn't use light at all, and just use pure electrical signals, then you're asking for a lot more trouble. I'll give you a flavor of sort of one of the theoretical proposals out there that proposes to make a valley filter. So, and that valley filter consists of a piece of graphene with a very narrow constriction here that has zigzag edges. Okay. Zigzag edges. Don't know how to do that. Right? This is very hard experimentally. So what do we do? So perhaps there is a way. Perhaps topology comes to the rescue. So what I want to show you today is a way of using topology, in fact, to create another valley contrasting properties that we can manipulate. And that is, we want to first generate one-dimensional wires that are valley momentum locked. So electrons with one valley index goes one way, electrons with the other valley index goes the opposite way. So I'm changing a 2D system to a 1D system over here. And then I want to show you how we manipulate these channels. So I've got 4 coming together in a cross, and I want to show you some guiding of electrons in this 4-way junction in the concept of a valve and a tunable electron beam splitter. Okay, all right. So topology. How does topology help you pick out another Valley contrasting property? So I take a page from the known topological physics. That's a quantum spin Hall effect. Spin Hall effect. Spin Hall effect is like Valley Hall effect. You send a current in, and because of spin orbit coupling, electrons with opposite spin polarizations go to opposite side of the sample. This is another optical detection. In fact, Faraday rotation exactly. How do you make a quantum spin Hall effect? You take a material, a small gap semiconductor material with a strong spin orbit coupling. You invert part of the gap in some part of the momentum space, as I've drawn over here. See, it looks like part of the conduction band ended up here, and part of the valence band ended up on the conduction band. Okay? So I've made a twist in that band structure there. I've made a negative gap, what we call a negative gap, in this material. The interesting thing is, when you take this and have it interface with vacuum, which is a trivial insulator with trivial gaps over here, interesting things happen at the sample boundary. What happens at the sample boundary is we end up with dimensional metallic channels that are spin momentum locked, just as the way we're drawing here. You can see the spin up electrons are going this way on this edge, coming back that way on this edge, and the spin down electrons are doing exactly the opposite. Right? So here I've locked the momentum and the spin of the electrons together. I've generated one-dimensional channels. What's even better is that if you don't have magnetic impurities in this material, you can't scatter between the spin up and spin down easily. These wires are ballistic. They don't have resistance. So you have very nice wires, right, when they're topological. So can you do something like this for Valley? You create Valley momentum locked wires and somehow manipulating those for electronics. So the answer is yes, you can. Right? That's what I'm talking about here. How do we do that? Think about the Bilayer Graphene band structure I've told you before, which had no gap. We opened up a small gap, reasonably big gap actually, with an electric field, right? And then I can just invert the direction of the electric field, and I would end up with a negative gap, right? I can invert the gap. So now you're probably thinking, what happens when you put the positive and negative gap together, just like what we did with this quantum spin Hall effect? So you end up with topological conducting channels in that junction. So this is how it's proposed. So I have a Bilayer graphene, that's these 2 blue sheets here. On one side, I'm applying a positive electric field. On the other side, I'm applying a negative electric field. My gap changes sign over here, and in the middle, in this junction here, theory tells us, this was first done by Eva Martin and collaborators, that we ought to have counter-propagating channels inside this junction. We carry K and K prime indices, and K goes out of the board, K prime goes into the board. There you go, you have your Valley momentum locked conduction channels. So their wave functions live inside this junction here. That's K and K prime on top of each other, but they have different value indices. So if you can make sure they don't scatter, then you have ballistic conduction. So these are in fact signatures of what's called the quantum Valley Hall effect. analogy to the quantum scheme or effect. And because they happen in the middle of the sample, we call them kink states. They're not actually at the sample boundary. They are patterned by gates. So we can pattern a lot of them. It's a scalable system here. Okay, you might be wondering why you got 4 pairs. This 4 comes from, in fact, counting the topological invariant, called the Chern number. I'm not going to go through this. If you're interested, ask me later how the 4 comes about. This is to show that it's topological in origin, and we have a way of tracking how many modes there are. So in this case, there's a 4 going into the board, 4 coming out of the board. 2 is due to spin, the other 2 is due to the 2 layers of the bilayer. Okay, so experimentalists may be wondering, you're not going to make an arbitrarily sharp junction, right? So we're patterning this lithography. So if this junction is wide, what happens? As long as it's not too wide, you're okay. So our colleague in the USTC had done some calculations of band structure, E versus K, for us for a junction that's, say, 60 nanometers wide, 70 nanometers wide. These red lines that I'm showing you here are these kink states, E versus K. And you can see that the group velocity is in one direction here and the opposite direction in the other value. They live inside a gap, delta prime here. Delta prime in our system is typically a few tens of millimeters. We can open up a larger gap. This can go up. 250 millimeters is sort of the limit that the band gap of Bilayer Graphene imposes. Ignore these lines over here. That's an artifact from the calculations. So these states are chiral in each valley. I've now put chirality and valley sort of locked together. And as I said, if you can prevent scatter from K to K prime, then you make them ballistic. So scattering from K to K prime involves a large change in momentum, 1 over the lattice size. So that's typically done by an atomic impurity. And I can tell you from many different ways, there's no atomic impurity in Bilayer graphene. Very, very pure. Turns out there are other higher order physical processes that could mix the valley together. But if you work hard enough, make your device very clean, there are conditions under which these guys can go ballistic. It's not as simple as just not having atomic impurities. Again, if you're interested in more of the physics, ask me later. This is how I'm going to represent these states, right? Minus, plus, and then these counterpropagating channels. Okay, a little bit more. So our experiment has a built-in control. You put the electric field on both sides in the same direction, there is no kink states anymore, right? No band inversion anymore. So you can contrast these 2 band structures, and when we do our experiment, we're going to compare results obtained here in the gap, results obtained here, to tell us whether it is really physics coming from these states or coming from something else. So this is we call odd, this we call even. Okay. Something else a little bit more. Okay. Since now you can flip these 2 polarities around and make a plus minus. So that turned the whole thing around. Okay. So I turn the chirality of the K and K prime around as well. Okay. You see it's going this way, now it's going this way here. Okay. In other words, I can make 2 helicities out of these states, plus 1 and minus 1. This will be important. You can think about what happens when you put them together. Okay, so what happens when you put them together? Well, if you align the helicities over here, my chiralities also align. So states in K can go through without changing the value index. Whereas if I put the helicities in the opposite. For my electron to keep traveling in the forward direction, it has to flip the value index from K to K prime. If you can prevent that from happening, then you prevent current from going through. So in this case, the valve is on. In this case, the valve is off. The way that works is very similar to how a spin valve works, right? Spin aligned, the valve is on. Spin anti-aligned, the valve is off. So this is valuable. Okay, so I've told you a whole bunch of things. Now I'm going to talk about how we actually make these systems and their properties and these few words on these valleytronic operations. So the way we make our devices, again, sandwich our bilayer graphene, these two blue sheets, in between hexagonal boron nitride. We're going to pattern a pair of split gates on top, a pair of split gates. These are graphite sheets, actually, at the bottom, and leave a junction about 60, 70 nanometers. We're going to align these gates over here, and then we're going to use a bottom gate here to control the Fermi level inside the junction. Everywhere else, this gate doesn't work. It's screened by that, it's screened by that, but it controls the Fermi level inside the junction. So we're going to go from valence band through the band gap to the conduction band. And I'm going to position my electric field so that in this chunk here and in this chunk here, we're sitting at the charge neutrality point, and the system has a gap. So I want this to be insulating, I want this to be insulating, and I want to have the field opposite so that I have these kink states in the junction. And we're going to measure in this direction and in and out of the board. How do we do that? Actually, I'm going to divert first and talk a little bit about sort of what opportunities 2D materials bring. That's not there already in, for example, a high-quality gallium arsenide 2D system. So gallium arsenide is something I worked on as a grad student. We had very good samples. Very good samples comes with a whole entourage of different stuff around it. It's not at the surface. It's about a few hundred nanometers below the surface. So if you want to manipulate it with the electric field, with a gate, your dimension of your device cannot be too small. The electric field is soft, over a few hundred nanometers. So the devices that are made, state-of-the-art devices in gallium arsenide, tends to have dimensions that are on this order. The graphene, bilayer graphene, and all the other 2D materials gives us more to work with in that sense, in the lateral dimension. So, and this is thanks to pioneering work from Columbia. This is two papers, one in 2010, one in 2013, figured out how to stack different 2D materials, one on top of each other, by hand, in the lab, in the air. So this is showing a BN, graphene BN stack. You don't have to, you don't need an NP growth anymore. You do, if you want to make large sizes. But you can stack materials that don't want to grow on each other. So graphene and BN is really tough. So this enables heterostructures of different 2D materials, and a lot of us are using these techniques to create different heterostructures. Okay? So these guys are really very good at it. See, they can make a device that stacks 7 layers of 2D materials together. Use this to observe very cool physics. What I want to show is playing the lateral dimension. These are still big laterally. What we can do in my lab very well is to pattern lithographically in the lateral dimension and control the gating. So I'll show you an example of a one-channel device, one Kink channel. So we take a piece of graphite, a few nanometers thick. We etch the split gate out of it. And then we put a layer of boron nitride on top. We put a layer of bilayer graphene on top. We etch it into a whole bar shape with electrodes. We put a layer of BN on top again. We do electrons, and then we do the top gates. Okay. So that's all done in my lab with optical microscope and transfer and line and so on. So the result is something that looks like this. I showed you before. Different colors and different layers of materials. The purple stuff is one piece of Bilayer Graphene carved out. So we're going to measure in this direction, and then measure voltage in that direction. So we got a little more ambitious after that. We went ahead and made a device that has 9 gates, 3 levels. So 4 at the bottom, 4 on top, again aligned in this split fashion. And if we gap this 4 quadrants, we're going to get these Kink states. The purple magenta is what I do. Right? So we got now a cross device. And you think about how to route current in a device that looks like that. Right? So each one of them is about 300 nanometers long, and then this is a 70 nanometer. That's an optical image of it. You really don't see what's going on here because everything is sort of in a tiny little bit over there. How did we make this? So you take a piece of graphite, make your gates out of it, and then the crucial improvement step here is we take now a whole stack of BN, Bilayer Graphene BN. This makes much cleaner interface. We put it on top of this split gate. We do some etching, expose the edge. We make contacts. That's a one-dimensional side contact to these 4 channels. And then we put the top gates. Again, what you have to do is develop all these lithographic processes to do that. Right? So my student Jing Li, who's sitting in here, spent quite a few years working on this. Went through a lot of obstacles to make this happen. I just want to show some pictures of sort of what didn't work, and then what worked at the end of the day. So that's a quad split gate. That's at the center of that device that we're looking at. The critical thing is to align the top and the bottom. So we've developed a process for that. I'd be happy to talk to people interested in knowing. It's also written in the paper that we published. We did some tests here. So these splits are written by E-beam in 2 different sessions. And if you've done E-beam, you know that if you come back and write the same feature, they're not going to end up at the same place. They're typically off by, 50 nanometers or something. So we want them to align. So we develop a process for that. And we can align things to better than about 10 nanometers. So in X direction and in Y direction, they're both aligned. So that's critical to the experiment that I'm going to show. Our first generation, we had only 1 channel, and we did some survey, which I'm largely not going to talk about. But the smoking gun is that we see conduction inside the gap only if we created this odd gating geometry, where we expect the Kink states. We have large resistance when there is no Kink states, so we know that it's there. I've also learned recently that Professor Woo Jun Lee's group from Korea realized something similar to what we did using a similar device geometry, meaning gating. So I'm going to move quickly to this 4-way junction, because that's where the valve of the beam splitter comes in. So I'll orient you a little bit on how we operate this device. So we've got 4 contacts, 1, 2, 3, 4. These are gold. They don't actually touch the Kink states. They send current in through this triangle here, which we call excess area. This area is a piece of heavily doped bilayer graphene. And same here, same here. So we're sending current this way, and we're measuring voltages also. So we can measure just the north channel by dialing up these gates and heavily dope all of this area over here. Then the resistance becomes very small, becomes negligible. Then when we do that measurement, we only measure the top channel. So that's what this cartoon means. We try to keep the contact resistance the same. You see, we haven't changed this area at all. And you will see the benefit of that. You do the opposite, measure the south, we measure the east, we measure the west. In fact, we measure all around, and they can all be ballistic. So a little bit more of, this is supposed to be a prime, I guess, what happens, because you're going to see me turn on magnetic field. So what happens to everything I've told you so far in the magnetic field? So my band structure, this is B equals 0. When you turn on a field, the gap actually opens larger. And that's lambda level basically moving up. And that's a good thing. The larger gap you have, the more robust the states are, the more ballistic they are. Something else that happens is that inside the junction, the states, the conduction, the valence band now form lambda levels. So if I now ramp the Fermi level through the valence band gap conduction band, inside the gap, there's the 4e squared over h conductance. Resistance is h over 4e squared. If I'm in the valence band, whenever I hit the lambda level, I get another 4e squared over h. So this becomes h over 8e squared, h over 12e squared, and then so on and so forth. And you will see this in the experiment. Okay. So a piece of experimental data. So this is the channel over here. I don't know what happened here. You see sort of an envelope. That envelope is sweeping from valence band here to conduction band over there. So right in the middle is this gapped regime. And you can see from top to bottom, at high field, roughly starting from 4 Tesla, we have a plateau developing. That plateau is the resistance of h over 4e squared plus a contact resistance that we know and can derive from other measurements. So that's this regime over here. You can also see that as you move into the conduction and valence band, there's the h over 8e squared plateau, h over 12e squared plateau, h over 16, and so on and so forth. Something else you see is as you drop the magnetic field, your peak resistance is now lower than h over 4e squared, right? The 0 is, this plateau is kind of here. Right? Something else is also conducting. And that something else that conducting is hopping through these gapped places. They're gapped, but they're not ideally insulating. They have some resistance. So when I pass a current this way, it can also go that way, and it can go that way. We know this is happening because we can use our reference setup, the even configuration, to just measure that. And that's the result of that measurement. You can see that at low field, this is several tens of kilo, so it's not completely negligible. And that plus this h over 4e squared is going to give you something smaller than h over 4e squared. And that's what we are measuring. But if you turn up magnetic field, this resistance very quickly goes to hundreds of megaohms. The reason that is happening is because now you're making electrons going around in circles. So these cyclotron orbits prevents hopping from happening very effectively. That's something that's known in a lot of systems. So if you can kill all of these conduction, you get a plateau there. So putting all of that together, we can in fact determine what is the resistance of just the Kink state itself as a function of the magnetic field. It reaches ballistic at about 4 Tesla also, and it's about 7 kiloohms at B equals 0. So not quite ballistic yet at B equals 0, but getting much better than the first generation devices we have. And that comes from using the dry transfer process to create a very clean interface. So that's one channel. Okay? So now let's try this operation of this Valley law. So I'm going to show you experiments where I align the Valley index and where we anti-align the Valley index. Now I've shown you, okay, we can more or less keep inter-valley scattering at bay. Right? So this should not happen a lot. There should be high resistance in this configuration, okay? And low resistance in this configuration. So in fact, I have a movie. This is a movie from Ivar Martin to show what is an electron to do. Okay? So well, on state, you see that it goes through. Okay? Has to go through because there's no state here, there's no state here. That gap. So this is kind of like a straight waveguide. In this case over here, it cannot go through, but it could go sideways. Plus minus. So I have Kink states here and here. Okay? And if you track the orientation, the K comes in, it could go either left or go right. There's no symmetry breaking at B equals 0. It's a 50-50 split. But you can do a little bit more by turning on the magnetic field. Remember, magnetic field exerts a Lorentz force on a charge. And it also has to do with the direction of the current, right? So on the Kink states, magnetic field does a very cool thing. If you're sitting at the charge and you're trying to point, the wave function of the K and K prime are always on top of each other. Doesn't matter whether you have field or not. That's a symmetry requirement. However, if you now move into the electron regime, the wave functions of K and K prime start to separate from each other. And the way it goes, because K and K prime have different group velocities, they go to different sides. So you can see that here, that blue is slightly to the right and red is slightly to the left. If you go to the whole regime, you change the sign of Q, the opposite happens. If you change the sign of magnetic field, the opposite happens. We've tested all of these. If you go to larger Fermi levels, deeply electron or deeply hole, then the wave functions separate more. So to the degree that they could be completely separated, meaning the separation is larger than the width of their wave functions. And we end up with something that looks like that. So now if you're an electron, you're coming in, let's say, on the K. You can't turn right anymore because your wave function does not overlap with that branch. You can only turn left. If you're in this regime here, in the deeply electron regime, that same electron has to go right. In the middle, it could go 50-50, right in the middle here. Right? So as now you sweep the Fermi level with a gate, you can direct where that current is going from all the way to the left through 50-50 to all the way to the right. That's the tunable beam splitter. So in fact, that beam splitter is based on the chirality of the Kink states, which we type with the Valley indices, right, in our system. So I'll show you how these work out. So first the valve. So this is the on state of the valve. I want to first show you how each channel looks like. That's the north channel. We measure it by itself. That's the south channel that we measured by itself. You see they're almost on top of each other, including the wiggles. The wiggles come from contacts, which we kept the same. And then this is through both channels at once. That's the black curve. So each channel is 4e squared over h. Going through both of them, we still have 4e squared over h. This tells you that these states are traveling through the junction without losing their direction at all. There's no mixing. So that's a perfect transmission. When you lower the magnetic field, so that was at 6 Tesla. When you lower the magnetic field, we have more mixing now in the junction because the gap is getting smaller. Right? So we see our transmission going down to about 0.6 or so when it's at equal 0. So that's the on-state of the bulb. In fact, you don't have to make them go straight. So if I flip my gate this way, no state here, no state here. The only way that the Kink states can go is make a right turn. That's a left turn. And you see that both left and right turn give us roughly about also h over 40 squared resistance. So you can coherently guide these states through bends. And if you can do that with one bend, you can guide them through a network. So that's a waveguide. So in the off state of the valve, we've talked about the state cannot go through straight, but it could go either left and right. And now let me control that by changing the Fermi level in the magnetic field. So these three curves are plotting the current received by each one of these terminals. They're all getting measurements at the same time. And you can see that here always get very little current in the entire range. So it's not getting any current. That's the valley bulb blocking. The east and the west show an X meeting in the middle, about 50-50. That is the electron beam splitting working. At very deeply hole regime, this side is getting all the current. It's very deeply electron regime, this side is getting current, and they sum up to about 1. In the middle, it's 50-50. So how well can this thing work? So the bulb works all the way down to B equals 0. The blocking effect always is there. We have about 8% of transmission at B equals 0. So if you take that and about 60% of transmission in the on state, this gives you about an on-off ratio of about 800%. Becomes a lot better when you turn on the field. Okay. But that's what happens at B equals 0. So kind of modest compared to CMOS ratio, many orders of magnitude. Comparable to the state-of-the-art spin bulbs. As far as a bulb goes, you don't actually, if you want to do a memory, you don't actually need a 10 to the 9's on-off ratio in order to do something like that. And I'll talk a little bit towards the end, one of the ways of improving it. The splitting works only in the magnetic field. So remember, we're using that. So the range of the tunability saturates to about 0 to 100%, about 5 Tesla. And then as you dial down the field, it becomes smaller and smaller, and then it's not there anymore at the equal zeros. So that's also to be expected. So there are actually ways of making that beam splitting without any magnetic field at all, and that's something we're working on. Theory, so we have a colleague, Chao-Xin Liu, in our department who helped us with explaining what's going on. And he developed a S-matrix model, and that together with Landauer-Hütteker, which tells you how 1D states transport, we could understand quite well our experimental data. So I'm actually getting done here. So I hope I've told you the operation of one type of valleytronic devices. These are things that we created out of Bilayer Graphene through gating. These valley momentum lock channels here that created another valley contrasting physics property. The chirality of the channel is locked to its valley index. And we can do a bunch of manipulations, do cool things with these channels. In particular, I showed you how we guide the current in a four-way junction. Look like this. I showed you how the valley wall work, and also how you can partition current between different terminals. So as I mentioned a little bit, oh wow, it would be nice to have a larger on-off ratio, yes. So that's something that we are working on. There are several ways of getting there. We can further increase the gap size, and that's a very effective way of doing so, making the sample cleaner. Also, we're working on things like splitting without a magnetic field at all. There's mechanisms for doing that. And we always try to think, because all of the experiment I showed you happens at 1.5 Kelvin. Can we raise the operation temperature? If we have a larger gap, we can probably do some of that. And we're going to test the limits of how high can we go, what are the performances we're getting. So that's something that will happen in the future. Important people, all the work that I've showed you here is done basically by this guy, G.E. Fantastic experimentalist, just defended his thesis. Our theory collaborators, Professor Zhenhua Qiao's lab from USTC, Professor Chao Xin Liu's group from Penn State, and these very nice hexagonal boron nitride came from NIMS Japan. Our funding resources, some other topics that we are working with, and always you're welcome to come to talk to me about any of these, and I'm happy to answer questions. Thank you, guys.
Any questions online from the people listening in? Go ahead and type them in the chat box. While you're typing in chat questions, we'll take a couple questions here on site. So anybody have a question?
The wavelength of the Kink states, are they spread throughout the channel or are they localized?
So they are about, I showed you a graph. I think the full width at half maximum is about 20 nanometers. For a junction, that's about 70 nanometers wide. They get a little bit wider when you have a wider junction, but they don't go down to zero, even if you have a very
So it's dependent on the geometry or dependent on the gate voltage?
I'm not sure. It definitely depends on the junction geometry. If you open up a gap, do you squeeze them a little bit, right? Yeah. I would imagine you probably do.
Yeah, what I'm trying to get at is what determines the length scale of how narrow you need to get, how narrow the channel needs to be to get these Kink states.
How narrow? Okay. So I'll show you this graph. In theory, it's always there. It's just practically, can you tell it from the other states that are around it, right? So I speak about, enlarging the gap is really a way of improving the performance. And you can see Okay, so this calculation is done. I didn't write it on the slide, but this junction has 110 nanometer in width. This is the original band gap in the bulk. When you have 110 nanometer wide, the junction, the gap that you're operating with is about 1/3 of that. If you go wider, then this becomes narrower.
So it depends on how fast the back, the gap closes.
Right. The 30 would be fantastic. 30 is very challenging lithographically.
So you guys are, you mainly spoke about like the challenges of physically getting the small gap. Mm-hmm. Are there also like in your device like electrostatic considerations for?
It was weak. That's why we stopped at where we were. So, practically speaking, I think with our BN, we could sustain probably about 100, about 200. The largest we can do is about 200 millidB in bulk. Then, depending on the junction width, normally we have 60, 70 nanometer wide, which means we would end up with about 100 millidB there. In that experiment, we had probably about 30. So we have a lot of room just by increasing the gap. I think one would probably already get complete ballistic transport without any magnetic field, and your on-off ratio should improve a lot.
So I was mainly thinking of, I guess you're using this global path gate to tune your Fermi level in the gap.
Right.
But like, what about like the band bending lengths due to like, you know, the thickness of the dielectric and those sorts of things?
What about it?
So like in, you know, in the case of like the 2D MOSFETs, you know, the thinner dielectrics and the thin 2D materials gives us these very, you know, narrow band bending lengths and better electrostatics. Do you have like similar considerations in your device?
I'm not sure what you're talking about. We have a thing that's a 300 nanometer way. What it does is it doesn't give you a uniform gating in this whole junction. But we're dealing with one-dimensional state with really only sort of maybe 10, 20 electrons. So I don't think that consideration completely applies. I kind of see what you're thinking about. Putting it much closer, I don't think will change a lot of things.
One more question? Anyone else? If not, thank you, June, for your webinar.
Thank you, guys.